Hello, I am Alexandros Bakas from Tampere University, and I will be talking to you about our paper Attribute-Based Symmetric Searchable Encryption that I co-authored along with Hai van Dank and Amtsad Yula from the University of Westminster and Adonis Michalas from Tampere University as well. So the outline of this paper is as follows. First, we talk a little bit about the background elements of SSE and our motivation for this work. Then we present briefly our attribute-based symmetric searchable encryption scheme, which is followed by its security analysis. Finally, we conclude this presentation by presenting some experimental results of this work. So, a generic symmetric searchable encryption scheme would look a lot like this. We have two entities, Alice and Bob. Alice is a user, while Bob here plays the role of a cloud service provider or CSP. So Alice has a sequence of plain texts which she encrypts to produce an encrypted database that consists of a sequence of ciphertexts along with an encrypted index. As a next step, Alice sends the encrypted database to the CSP where it will be stored. Now, at a later time, if Alice wishes to search for the files that contain a specific keyword, she can issue an encrypted query that contains the keyword and send it to the CSP. Now, the CSP can locate all these files that contain the keyword W without knowing neither W nor the contents of the files. So as soon as the CSP locates all these files, it sends back to Alice an encrypted result. And when Alice has the encrypted result, she can decrypt it locally and get the plain text files that she was looking for. The problem with this generic approach of SSE is that when Alice gets back the encrypted result, she gets access to the entirety of the file. So if we assume that the encrypted files are, for example, medical data that contains sensitive information about some patients, we would not want Alice to access the whole document, but only those parts that she's authorized to. Now, even though there are many works on the field of SSE, we have identified a gap in the literature when it comes to symmetric searchable encryption and access control. And this has been our main motivation for this work. So our goal is to make it possible for the user to retrieve just some parts of the encrypted data and not the entirety of the encrypted files. Now, if we look at an example here, Alice takes the role of a researcher and queries an encrypted database that contains sensitive information about some patients. So, just like before, Alice issues a search query, but this time she only gets back these values that correspond to the age and the disease of the patient and not the name of the patient. So this way, if Alice is indeed a researcher, she can perform some statistical analysis on the database without leaking the privacy of the patient. Another contribution that we make on this work is that we enhance our scheme with the crucial notion of forward privacy. In a nutshell, forward privacy is a property that makes it impossible for the server to link newly added keywords to previous queries. So if we look at an example again, we assume that at time 1, Alice adds file f1, it contains keyword w1 to the cloud. Then at time 2, she's searching for those files that contain the keyword w1, and naturally she gets back f1. And at time 3, she adds a new file f2 that also contains the keyword w1. So we do not want the server to learn that the update during time 3 is for the same keyword as in times 1 and 2. To put it a little bit more formally, an SSE scheme is said to be forward private if and only if the leakage that is associated with the addition operation only leaks the nature of the operation as well as the file identifier. Now, coming to our construction, our system model has three main entities. First of all, we have the users, then we have a trusted authority, that is trusted execution environment enabled. It means there's a TA running on the trust authority, and TA is an entity residing on the cloud. And then we have also the cloud service provider or CSP. Now, to enable the users to perform the search operation or the addition operations they want, both the TA and the CSP have to maintain some indexes. So first of all, TA maintains an index, a number of files index that contains a mapping between masked keywords and attributes with the number of files the keyword of the specific attribute is in. Apart from that, it maintains a number of search index that contains a mapping again between masked keywords and attributes, along with the number of times the keyword of the specific attribute has been searched for. Now, on the CSP side, we have the encrypted index, the dictionary, which is a mapping between file identifiers and masked keywords. Then we have the actual database that consists of the file identifiers, the attributes, and the ciphertext of the keywords. And then we have two more tables, roles and rules, that maintain some mappings between roles and some binary vectors, or attributes and binary vectors. And actually, these two tables, roles and rules, help us into achieving the access control that we want. To better understand what we're doing here, let's assume an example with three different roles: doctor, nurse, and researcher, and three different attributes: surname, age, and disease. Moreover, we assume that a nurse wishes to search for the surname of patient. So, in this case, we'll look at the binary string that is associated with the role of the nurse, which in this case is 010, and then we'll look at the binary string associated with the attribute surname, which is 011. Finally, we calculate the logical conjunction of the two binary strings, and if it's not 0, as in this case, then the nurse can indeed search for that specific attribute. Now, if instead of the attribute surname, the nurse wanted to search for the attribute age, then the conjunction of the two strings would be 0, and hence the nurse would not be able to search for that specific attribute. Coming on to the actual algorithms of our protocol, of our scheme, first of all, we have a key generation algorithm in which the user Alice generates K1, which is an encryption key, which she uses to encrypt her actual files. And then we have K2, which is a verification key. We'll see how this is used in the few slides. K2 is shared between Alice and the TA. The key sharing protocol is not in the scope of this work, though. Now, Alice starts adding files to the CSP. Now, what's important to note here is that our work works with structured data of the form attribute keyword, and so on and so forth. So to add an attribute keyword pair to the cloud, Alice first requests the corresponding number of files and number of search values from the TA for that specific attribute keyword pair. Now, as soon as she gets these values back, she can encrypt her file, and then she sends to the CSP both the index and the database, an encrypted database. So, as we said before, the dictionary dict is a mapping between file identifiers and hashed keywords, while the actual database consists of the file identifiers, the attributes, and the ciphertexts of the keywords. Now, if we look a bit closer here on the dictionary, we see that we see a weird KW in there. So this KW is a unique keyword key that is associated with the number of search values for a specific keyword attribute pair. So it is natural that on every search operation, this keyword key changes as the number of search value is incremented by 1. Now, after the CSP receives this information, it updates its local database to maintain all this new information. Finally, Alice sends an acknowledgement to the TA to increment the number of files for that specific keyword attribute pair by 1. Now, to search for a keyword attribute pair, Alice starts again by requesting the number of files, number of search values for that specific pair from the TA, and then she sends the search token to the CSP. So the search token consists of the unique keyword key for the keyword that Alice is looking for, then the number of files for that specific keyword attribute pair, and finally a hash of an updated keyword key. So this hash of the updated keyword key is actually the new addresses on the dictionary. So in each on each search operation, the addresses for the keyword attribute pairs are updated and based on KW. And this is actually how we maintain the notion of forward privacy on our construction. As you can see here, KW prime is actually exactly the same as KW, with the only difference being that there is a different number of search value at the end of the concatenated terms. Now, as soon as the CSP receives the search token, it sends KWJ to the trusted authority. Now, having KWJ and the verification key K2, the trust authority can compute the hash of the keyword key prime as well and send it back to the CSP. The reason we add these extra steps in our protocol is because we want to make sure that the user is sending the correct updated addresses to the CSP. So if we assume that Alice is a malicious user, she could send wrong addresses, and then that would render the database inaccessible to the rest of the users, as they could not create consistent search tokens. So when the CSP receives the updated information from the TA again, and if it is the same as the ones received by Alice, it updates its database accordingly, sends back to Alice the keyword attribute pairs that she was looking for, and finally sends an acknowledgement to the TA to increment the number of search times by 1. Now, moving on to the security analysis of our construction, we make use of the real ideal world formalization. In particular, we assume that our adversary can observe the real world, that means the real protocol, the real algorithms with the real inputs and the real outputs. And we try to design an ideal world where instead of the real algorithms running, the simulator simulates the whole procedure. Now we have the restriction here that the simulator can only be given as input what is leaking from the real world. That means that to simulate addition tokens or search tokens, the simulator can only be given as input the leakage from the addition or search operation, respectively. And our goal is to simulate the real world in such a way that it will be indistinguishable from for the adversary. Indeed, we managed to build such a simulator. So these are the real and ideal worlds. If you see, they're exactly the same, except for lines 4 and 6, where in the real experiment, the search and addition algorithms take as input the correct input. In lines 4 and 6 of the ideal world, the simulator takes as input the leakage from the search and addition operations. More information on that can be found on the actual manuscript. So, comparing our work to different works, we see that the only work that achieves better search time than ours is a scheme that is static. Moreover, our paper is the only one that provides an access control mechanism. Now, what's important to note here is that the concept of enabling access control in searchable encryption is not new. However, all the existing works on access control and searchable encryptions are only in the public key setting. So our work is amongst the first that provide an access control mechanism in the symmetric key setting. Now for the experiment section, I will let Ivan Dank continue with the presentation. Thank you very much from my side.
I'm Ivan. I continue to Alex to present about the experiment. In order to conduct the experiment, we set up 3 separate virtual machines in OpenStack Cloud for 3 components. The web server will serve the services for users to upload and search files, the trusted authority, and the CSB. All the machines have the same configuration with 4 virtual CPU, 8 GB RAM, 80 GB disk, and Ubuntu 18 as the operating system. Additionally, we have a test machine with a 4-core CPU, 8 GB RAM, 250 GB disk, and Ubuntu system. This test machine is to generate automatically the request sending to the web server. So because of the data content is not really important for the performance test, so we generate the syntactic data as JSON format with 300 instances, and the number of attributes vary from 50 to 400. For implementation, we rely on Stanford's JavaScript crypto library to implement the cryptographic functions at the user side. We use the Django framework and TestDB to set up the web services and REST API services, and we use both REST-SQL for database. And finally, we use the APT Trimeter with Selenium to generate automatic request and method time. For each request, we run it 30 times and calculate the average. So in the experiment, we aim at firstly evaluate the impact of the number of attributes verified to the search time, and then evaluate the impact of the size of the result list to the search time. The search time in these scenarios is a sum of processing times at the user side, at the server side, and the communication time. So we can see in the figure that when the number of attributes verified increase, then the search time increase. But it is only clear when the number of match keyword found is high. The reason is the main difference is the time to decrypt the received data when there are more results. And it can be seen more clearly in figure B. When the number of file occurrences increase, then the processing time increase. The next goal is to measure the time required to insert new data in a non-empty database. So we have two scenarios. The first scenario with 300 files in the database, and the second scenario with 50 files in the database. And there is no much difference between the two scenarios when we add one file in the two databases. But when the number of attributes increase, then the processing time to add a new file increase. The reason is because when the number of attributes increase, we need more time at the user side to encrypt the data. And finally, we measure the data storage overhead of the scheme compared to the storing plain text data. So the blue line is the size of the data in plain text, and the green line is the overhead at the trust authority. That is the size of the indexes stored at TA, and the orange line is the size of the encrypted data plus the indexes stored at the CSV. The yellow line is the sum of the data size stored at CSV and T8. So we can see that the difference between the scheme and the plain text data storage is the difference between the blue line and the yellow line. And that's the end of our presentation. Thank you very much for your listening.